This is Math 1710, Section 4.3 on logarithmic functions. The expression log base A of x actually is an exponent to which the base A needs to be raised to obtain x. So I'm going to let this equal y, and I like to draw arrows like this. A to the y power is equal to x. A to the y is equal to x, where A is the base, y is the power to which that base is raised, and x is the value that you get when you raise it to that power. So over here we can do the same thing. This is the base, this is the value, and this is the power. So this base raised to this power gives you this value. So looking at some examples under number 3, part A says log base 3 of 81 is equal to 4. We are asked to write the exponential equivalent. So if we go 3 to the 4th equals 81, we have it. 3 to the 4th equals 81. And of course 3 to the 4th does equal 81. The second one, log base 3 of 1/3 equals -1. So 3 to the -1 equals 1/3. And that is true, because when you have a negative exponent, to make it positive, you move it across the fraction line. So this is 3 to the 1, or just 1/3. The third one says log base 10 of 0.01 equals -2. So 10 to the -2 equals 0.01. Because 10 to the -2 is the same as 1 over 10 to the 2, which is 1 over 100, and 1 over 100 is 0.01. Examples under number 4 says 6 to the 1/2 is equal to the square root of 6. So this is already in exponential form. We want to write it in logarithmic form. So we're going to go log, the base is 6, the power out here is 1/2, and it comes out to the square root of 6. And it is true that 6 to the 1/2 power equals the square root of 6. They are equivalent. That's part A. Part B, e to the 0 equals 1. Log, the base is e, the power is 0, so that goes out here, and the value is 1. E to the 0 equals 1. And in fact, anything to the 0 power equals 1, of course. 2 to the 5th equals 32. So it's the log, the base is 2, the power is 5, and the value is 32. All right. Under part B, it tells us that logarithmic equations are equations with a logarithm in at least one term. So an example would be log base 4 of 1 over 64 equals x. So there's a log right here, so that makes the whole equation logarithmic. Now we're going to look at some examples where we solve logarithmic equations. Under number 3, part A, we have the log base x of 8 over 27 equals 3. Now, normally when you have a logarithmic equation, to solve it, you turn it into an exponential equation. So that would be x to the third equals 8 over 27. We can then raise both sides to the 1/3 power. 8 over 27 to the 1/3 power, which is the same as taking the cube root. Cube root of 8 is 2. The cube root of 27 is 3. So the answer is 2/3. So the x here should be 2/3. The second example is log base 4 of x equals 5 over 2. So we're going to change it to exponential. 4 to the 5/2 power is equal to x. Now, we can change this into radical form. 4 is the base, we put that inside. The index is 2, that goes outside, and the power on the base is 5. Now 4 to the 5th power is going to be a very large number, so instead of doing that, we'll first take the square root of 4. Square root of 4 is 2, so that becomes 2 to the 5th, and that becomes 32. All right. Now, the next example is log base 4, or 49 rather, log base 49 of the cube root of 7 equals x. So 49 to the x power equals this value. 49 to the x power equals the cube root of 7. Now, in this situation, we're going to use a common base that relates 7 and 49. Of course, 49 is 7 squared, so we can replace 49 with 7 squared raised to the power of x. This right here is 7 to the 1/3 power. We're going to now raise a power to a power, and we're going to get 7 to the 2x power, and that equals 7 to the 1/3. Since the bases are the same, the exponents are the same. In other words, they equal each other. So 2x equals 1/3, and divide by 2, and x is 1 over 6. All right, under part C on this section, we're going to look at logarithmic functions as far as their graphs are concerned. And it's saying that the base has to be greater than 0, which means it's positive, but it can't be equal to 1. X is also positive. If that's all true, then f of x equals the log base a of x becomes a logarithmic functions, and the characteristics of that functions are that on its graph, you always have 1 over a as a point, comma -1. That's 1 point on the graph. Another point on the graph is 1 and 0. And a third point is a and 1. Whatever a is will be depend on whatever this a is, the base on that logarithmic function. If a is greater than 1, the function is increasing. If a is between 0 and 1, it's a decreasing function. And the y-axis is a vertical asymptote, which means the graph approaches the y-axis, but it never actually touches it. The domain is from 0 to infinity, and the range is from negative infinity to positive infinity. So we're going to look at some graphs on the next page here. The first one is f of x equals log base 2 of x. And I've already provided you a table for x and f of x, where f of x is the same as y. And I'm using 1/4, 1/2, 1, 2, 4, and 8 for my x's, because they're all some power of the base, which is 2. So I'm going to put 1/4 in here for x. So f of x then would be log base 2 of 1/4, and that'll equal f of x, or y. So that's 2 to the y, that becomes 2 to the y equals 1/4. 1/4 is the same as 1 over 2 squared, which is the same as 2 to the negative 2. So 2 to the y is the same as 2 to the negative 2, so y is negative 2. I'll do the next one as well. The log base 2 of 1/2 is equal to y, which means that 2 to the y is equal 1/2, which is the same as 2 to the negative 1. So 2 to the y is the same as 2 to the negative 1, so that means y is negative 1. So we put a negative 1 in there. And if you do the rest of these, you'll get a 0, a 1, a 2, and a 3. This point right here, the 1 and the 0, is the one of the 3 that I mentioned up there. The 1 over 2, the negative 1, is this point, and the 2 and the 1 is this point. So these 3 points right here, we can get by using this pattern right here. And we don't have to actually work it out doing it this way. So either way you can get it. If you plot those points on the coordinate system, your graph will look like, let's see, 1/4 and negative 2 would be about right there. 1/2 and negative 1 would be about right there. 1 and 0 is right there. 2 and 1 would be about right there. 4 and 2, and 8 and 3. So the graph comes around like this. This gets very close to the y-axis, but it never touches it. So there's the graph of the first one. And of course, you can verify this graph by using your graphing calculator. There is a button on your calculator called log. So you would go to y equals, type in y equals log base 2 of x. I'm sorry, you can't do that until I tell you something else later. So you'll just have to do it without using the calculator for now. All right, the next example to graph is part B here. F of x equals log base 1/2 of x. So my table, I'll use the same values for x: 1/4, 1/2, 1, 2, 4, and 8, because they're all powers of 1/2 in some way or another. And remember, you have 1 over a comma -1 is 1 point, 1 and 0 is another, and a and -1 is a third point. So 1 over 1/2 would be 2, so that'd be this point. So -1 for y. 1 is here, and that goes with 0. A is 1/2, and -1, that'd be this point. So these 3 points I can get by using this pattern that works for all logarithmic functions. So I will let you calculate the rest of these values just like we did under part A, and they will come out to be 2, let's see, 4 is a -2 and a -3 here. So 1/4 and 2. Okay. As I plot these, have 1/4 and 2 would be about right there. 1/2 and -1 would be about right there. 1 and 0 about right there. 2 and -1. 4 and -2. And 8 and -3. So my graph's going to come down this way. Because my base A is between 0 and 1, it's a decreasing function. Whereas in the last example where the base was 2, so it was greater than 1, which makes it an increasing function. Part C, f of x is log base 2 of x minus 1. All right, so our table, 1/4, 1/2, 1, 2, 4, and 8 for x. It turns out that these 3 right here are all undefined. This will be 0, this will be 1.585, and this will be 2.8074. And all you have to do is put these x's into the function and you'll find out that those values are true. So really the only ones we have are these 3. So 2 and 0 will be right there. 4 and 1.5, so it'd be about right there. And 8 and 2 point, so it'd be right there. So it goes this way, and it'll come down this way as well. All right. All right, that's part C. All right, we're going to go to the next section here, part D, properties of logarithms. If you remember, I said that a logarithm is actually an exponent. So that means that the rules or the properties for logarithms are very similar to the properties for exponents. So the product property says that the log base A of xy, which is a product, is log base A of x plus log base A of y. It's the same thing as like if you have x to the 4th times x to the 3rd. This is a product, and you add the exponents, x to the 4 plus 3, and get x to the 7. So product means addition. The next one is the quotient property, x over y, so you have subtraction. Just like if you had x to the 4th over x, it'd be x to the 4 minus 1, which is x to the third. Subtract goes with division. The third property is called the power property, which says that the log base a of x to the r power is equal to r times the log base a of x. So really you're taking this r and putting it out in front. It's like raising a power to a power. You multiply. And then there's two special values. The log base a of 1 is equal to 0 because a to the 0 is equal to 1. And log base a of a is equal to 1 because a to the 1 is equal to 1. So let's do some examples under number 6, part A. We have the log base 6 of 7 times 9, which can be rewritten as a log base 6 of 7 plus log base 6 of 9. So all we're doing is writing or rewriting this product as a sum of two separate logs, and that's called expanded form of a logarithm. Part B, we have log base 9 of 15 over 7. That's a quotient, so we're going to have log base 15, or log base 9 of 15, minus log base 9 of 7. So division is subtract. All we're doing is rewriting the expressions. Log base 5 of the square root of 8 is the same as log base 5 of 8 to the 1/2 power. The square root's the same as 1/2 power. We could take this 1/2 and put it out in front, and that gives us 1/2 log base 5 of 8. Part B, log base A of the square root, or the cube root rather, of m squared. So we can rewrite this in exponential form. Log base A of m to the 2 over 3 power. And we can take this 2 over 3 and put it out front using the product property, 2/3 log base A of n. I did E instead of D, so I'll do D now. Log base A of m n cubed over p squared t to the 4th. So we have a combination here, actually, of products and quotients. So what we're going to do is do log base A of m plus log base A of n plus log base A of q, and then minus log base A of p squared. But instead of writing p squared, I'll put the 2 out front here using the product, or the power property, minus log base A of t, and it would be to the 4th power, but I'll put the 4 out in front using the power property. So this single logarithm is written this way in expanded form. All right, we're ready to do F, which is log base B of the nth power of x cubed y to the 5th over z to the m power. So I'm going to rewrite this as log base b of x to the third, y to the fifth, over z to the m, all of that raised to the 1 over n power. So I changed it from radical form to rational exponent form. So I will now put this 1 over n out in front of this, and I'll put a parentheses to take care of everything in this parentheses. So that's log base b of x, but it's not x cubed because I can put the 3 out in front of this x, or this log rather, plus log base b of y. Normally I could put y to the fifth, but I'll put the 5 out in front here. Then I'll do minus log base b of z. Normally I'd put an m here, but I could put that m in front here. So I now completed the parentheses, and I can leave it like this, or I can multiply all this out and get 3 over n log base b of x plus 5 over n log base b of y minus m over n log base b of z. So either one of these is correct. Just have to be aware that you can write it either way in case you're given a multiple choice situation. Okay, so we're going to go now to some other examples where we are given the expanded form and we have to rewrite it into a single logarithm. So for 7a, we have the log base 3 of x plus 2 plus the log base 3 of x minus the log base 3 of 2. So here we have a plus and here we have a minus. So these two are multiplied, so that's log base 3 of x times x plus 2. And here we have a minus, so we can put all that over 2. So this is considered to be a single logarithm as opposed to expanded form of 3 logarithms. All right, the second, 2 log base a of m minus 3 log base a of n. Okay, this 2 can be put here, this 3 can be put here. We're doing the reverse of what we did earlier, so that's the same as log base a of m squared minus log base a of n to the third. Since this is a minus, that becomes log base a of m squared over n cubed. The next one is 1/2 log base b of m plus 3 over 2 log base b of 2n minus log base b of m squared n. So we can put the half on the m, we can put the 3/2 on the n right here, and we can put, well, there's no number out here, so we don't need to do any of that right there. So that's a log base b of m plus log base b of 2n to the 3 over 2 power, and then minus log base b of m squared n. So here we have a plus and here we have a minus. So that's log base b of m times 2, I'll put the 2 here, n to the 3 over 2, over m squared n. Now this can be simplified, so that'll be log base b, m divided by m squared. That puts the m on the bottom. And here we have n to the 1½ minus 1, so that's n to the 1/2. And I'll just put all that in parentheses. All right. Now we're going to evaluate some logarithms that we are given numerical values. So for number 8, part A, it says that, by the way, the log of 2, or base 10 of 2, is equal to 0.3010. We're going to use this to evaluate these expressions. Log base 10 of 4. Since we know the log base 10 of 2, we can rewrite the 4 as 2 squared. Then we can put this 2 out in front, and that'll give us 2 log base 10 of 2. We know what this is from over here, so that's 2 times 0.3010, which is 0.6020. So knowing the numeric value of one particular log, we can find other ones. The next one is log base 10 of 5. Now, the way that we get 2 out of 5 would be to rewrite this as the log base 10 of 10 over 2. Because that now gives us log base 10 of 10 minus the log base 10 of 2. And we looked earlier, this right here is equal to 1. So that's 1 minus this, which is 0.3010. And when you actually subtract those two, you get 0.6990. All right, there is a theorem here at the end of this section that says if A is positive, it's not equal to 1, just like we looked at before. A to the log base A of x is equal to x, and x is positive. And the log base A of A to the x is also equal to x. So those are just two identities that may be useful in solving or evaluating some logarithmic equation or logarithmic expression. This concludes this section. Thank you.